Hello, welcome to our video solution for problem 2 from quiz 3. This is a long one, at least the statement of the problem is long. So let's see, we have an enormous gas cloud traveling through space, and the astronomers are going to place the Earth at the origin, right, the 0, 0 of their coordinate system. And when they do that, they're able to model the surface of the gas cloud relative to the position of the Earth by this function. So they call it g of x, y, z, and it's xy minus z squared plus 1 is equal to 0. So this will give us some surface away from the Earth. They want to determine the location of the gas cloud that is closest to the Earth. All right, so you got the Earth over here on the side, nice purple Earth, and there's this gas cloud and it has some shape, and we want to know where on this gas cloud, right, is closest. And maybe the size of this thing is so big that we can treat the Earth as being just a point. All right, so even though we draw it like it's this big sphere, maybe in reality we're going to treat it as if the Earth is just a singular point. Okay, and so we want to know like where is it closest to the Earth? At what point on that gas cloud? And so let's see, the astronomers say, well, the distance from the origin, right? So this could be 0, 0, 0, to any point, so say this was the point x, y, z, is given by, well, you take the square root of the x squared plus y squared plus z squared. This is just the distance formula, or if you like, the Pythagorean theorem. But because square roots are annoying, the astronomers say, why don't we just square that function? And because we know the square function is an increasing function, we might as well just minimize the square. So the square would just be x squared plus y squared plus z squared. So if we can minimize this function d, subject to the relation, right, that or the constraint that you need to be in this gas cloud, right? We don't care about minimizing the distance to any point in space. That would just be 0, right? The Earth is very close to itself. But we want only points that live on this gas cloud, which means they satisfy this equation. All right, and then finally, we're given instructions to use the method of Lagrange multipliers to find the location of all the points on the gas cloud which are closest to the Earth. So here we go. We are going to want, using the method of Lagrange multipliers, to compute the gradient, not multiplies, but multipliers, the gradient of this distance function. Right? It's really the square of the distance function. All right, so the gradient will just be 2x, comma 2y, comma 2z. Taking partials is pretty easy with this. All right, then we want to figure out where this squared distance function is parallel to the vector, to the gradient of this surface. So let's copy down here, g of x, y, z, just so we have it, is xy minus z squared plus 1. So to be parallel, right, we need this to equal some lambda times g, where lambda is what we call, not g, but the gradient of g. Lambda is what we call the Lagrange multiplier. So let's see, if we take the gradient of g, we're going to get y, and of course there's a lambda, so we get lambda y. And then with respect to y, we're going to get x times a lambda is lambda x. And then with respect to z, we're going to get a negative 2z times, again, this lambda. Okay, so now we want to determine when these two vectors are equal to each other. All right, so let's see, if they're going to be equal, then 2x is going to have to equal lambda y. So 2x equals lambda y. And 2y will have to equal lambda x. And 2z is going to have to equal negative 2 lambda z. All right, well, the last one, I mean, I just can't help myself. I want to divide by 2, like right off the bat. So z is equal to negative lambda z. And we'll mess around with that in a little bit, but let's head up to these top two. So this is a pattern that we've seen a few times where you have an x on one side, a y on the other, and then down below the y on one side, the x on the other. And wouldn't it be great if we could just kind of toss them all in together at once, right? So we have x's and y's everywhere. So what we can do is multiply this top one by y. So that I'll get 2xy is equal to lambda xy. And then let me multiply this middle one by x. So that I get 2xy is, sorry, we multiplied this one by y. So this is y squared. We multiply this by x, we get lambda x squared. So the beauty is that now lambda y squared is equal to 2xy, and 2xy is equal to lambda x squared, and so the lambda y squared has to equal the lambda x squared. Okay, so we don't divide, right? That was one of the pitfalls. I'll subtract instead of dividing, because when I subtract, I'll be able to factor out a lambda. And I'll get lambda times y squared minus x squared equals 0. And the reason why I didn't want to divide is there's a possibility that lambda maybe could be 0. And if lambda is equal to 0, that would be a bad thing, right? So this allows us to note lambda could be 0 or y squared could equal x squared. All right, we do the same thing down here. If I add, I can factor out a z. So I'll add plus lambda z to both sides, factor out the z, and I'll get 1 plus lambda is equal to 0 when I multiply by z. And so again, I have a product equaling 0. And so either z is 0 or 1 plus lambda is 0, which means lambda would be -1. Okay, so we have a bunch of possibilities. And there's one thing we haven't brought into the game yet, which is we need to be on this curve or the surface, right? G equals 0. So whatever choice we make, we're going to have to compare it with this function as well. So let's just take these systematically. Let's look at what happens if lambda was equal to 0. Well, in that case, we go back to the original equations. If lambda was equal to 0, then I would have 2x is equal to 0 times y, which is 0, which would mean x is equal to 0. Okay, but similarly, 2y would equal 0, so y is 0. Okay, so what then would happen with our z? Well, in this case, we again have 0 on the right, so 2z would equal 0, and so we would have z is equal to 0. So actually, every single one of our components has to be 0. But let's check to see if that actually is on the surface itself. So if I evaluate g at 0, 0, 0, I'm going to get 0 times 0 minus 0 squared plus 1. But this is equal to 1. Which means that this is not on the surface, so we don't get what we call a constrained critical point. Okay, so 0, 0, 0 is not on the surface, so is not a constrained critical point. So if lambda is equal to 0, we just don't get anything useful, so that's not one of the considerations. Okay, so we must be in the situation where y squared is equal to x squared. Okay, fine. Well, I mean, we can immediately write something from here, perhaps, or we could use the second equation. Let's see. How about we just use these, right? We have all these options. Let's try it, right? Because we need all, one of these has to hold and one of these. So I don't know. Let's say we had z was equal to 0. So if z is equal to 0, we can head back up, use our surface. We have this, we know xy minus z squared plus 1 is 0. So let's write it, xy minus z squared plus 1. And oh, hey, z is 0. So I actually can just make this xy plus 1. So this would tell me that x times y is equal to -1. All right, well, if x squared is equal to y squared, like how does that actually happen? Well, in the real numbers, right, the only way that happens is if y and x are the same, or if y and x are opposites of each other. Okay, so y could either be x or y could be -x. Okay, so what if y was equal to x? Well, if y is equal to x, then x times y will be just x squared, which is certainly not going to be a negative number. What if y is equal to -x? Well, then you'll have -x squared as a negative number. Yeah, that actually could happen. Okay, so y is equal to x, then we would have -1 equals x times y equals x times x, which is x squared, and this doesn't happen. And if y is equal to -x, then we'll have -1 equals xy equals x times -x, which is -x squared. And this can happen provided that x is either plus or minus 1. Right? Drop the negatives, you'll have x squared as 1. All right, so we actually get some constrained critical points in this case. So if x is 1, then we know y will be -x, so we'll get -1, and z is 0 in this case. If x is -1, y again is the opposite. We'll get +1, and z is still 0. All right, so the other situation was that lambda could be -1. So let's go back up, take a peek. When lambda is -1, we're going to get that 2xy is going to equal -y squared, and also -x squared. All right, so the other situation was it could be that instead of z being 0, we could have lambda equal to -1. So in this case, if we head back up, we have this relationship, 2x will equal -y, and 2y will equal -x. So let's see here, we have 2x is equal to -y, and 2y will equal -x. Now this top one lets us know that y is going to equal -2x. However, we also knew from up above that y squared equaled x squared, which meant that either y was x or y was -x. So yeah, that's a little bit concerning, isn't it, right? So we know that y equals x or -x. Well, whether it equals x or -x, you're going to have an equation that's going to tell you x is 0. So if you have x equals -2x, then that'll tell you that 3x equals 0, so x equals 0. Or if you had -x equals -2x, then you could add 2x to both sides and you'll just get x equals 0. So either way, we get that x is equal to 0. And of course, once we know that x is equal to 0, then we know that y equals 0. So either one implies y equals 0. All right, well, what about the z? We know nothing about the z here. So what do we know? Well, the equation 2z equals -2 lambda z, when you make lambda -1, you just get 2z equals 2z. That doesn't tell you anything. However, we still have the surface. And now that we know both x and y are 0, let's put that in. So when x equals y equals 0, well, let's get that in a y. There we go. Now we know that 0 is equal to xy minus z squared plus 1 is equal to, well, just kill the x and the y. You just get -z squared plus 1. So we'll add z squared to both sides, and we get z squared is equal to 1, and so z is equal to plus or minus 1. And so we get another couple of constrained critical points. In both cases, the x and y are 0, but now the z could be plus 1, or the z could be minus 1. All right, so in total, let's see. We found something which looked like it was going to be a constrained critical point, but it wasn't on the surface. So that didn't work. Then we had two more constrained critical points, one -1, 0, and -1, 0. Along with two more coming from our other situation, 0, 0, 1, 0, 0, -1. Now, our goal is to figure out, of these 4 points, right, which all lie on the surface, which of them is closest to the origin. That is, which of them minimizes our original square of the distance function, which just said square all of the different components. So we can evaluate this at either, well, let's see, we have 1, -1, 0, and you just square them. 1, 1, and 0 gives you 2. And the same thing with d of -1, 1, 0. That will also be 2. How about these two? Well, d of 0, 0, well, it doesn't matter whether we use plus or minus 1. When you square, the plus or minus will go away. You get 0 plus 0 plus 1 is 1. And so these are the 2 points which are going to be closest to the Earth.